All right, so what's the plan? So let's do another example problem for conservation of mass. And we're going to follow the general structure for problem solvings that we did last time. First, we're going to organize our problem info. Then we're going to define a control volume. Then we're going to break up the surface of our control volume into pieces. Then we're going to do integrals on the right-hand side of the conservation of mass equation. Then we're going to deal with the left-hand side, whatever may become of it. Then we're going to do some algebra and organization of our results. And then we're going to do some checks. So this is going to be our problem-solving strategy for these conservation of mass type problems. Only this time, we're going to do a slightly trickier problem. So let's get started with organizing our problem info. So let's imagine we have a pipe. Let's say it's a cylindrical pipe. Maybe looks something like this. And I'm flowing some flow into this pipe, and I have information about what the velocity profile is in this pipe. So, later on in this class, we'll actually derive we'll derive how we get to this velocity profile, but for now, just pretend that the clouds opened up and Professor Lannin's face poked through and said, the velocity profile is this, and then the clouds closed back up. So, what is that velocity profile? It turns out that flow in pipe tends to be parabolic, where you get the maximum velocity at the center of the pipe, and the velocity goes to 0 at the edge of the pipe. Remember, the edge of the pipe isn't moving, so the fluid immediately next to the pipe isn't moving. But we have to have some flow, so the flow kind of bulges out in the center and then goes back. So let's say we knew what this velocity profile was, and we wanted to say, hey, what is a relationship between this velocity profile and the volumetric flow rate going through? So let's say, clouds opened up and we had this information about the velocity profile. Let's say we wanted to say, hey, for this particular velocity profile, what is the volumetric flow rate? So when we think about relating things like velocities to volumetric flow rates, this is going to invoke conservation of mass, and it's going to be a little trickier than some previous conservation of mass problems that we've done, because now we have a non-uniform velocity profile. So the previous example problems that we've done, we sort of had we had velocity basically being uniform, like all some amount, or we just were dealing with straight up volumetric flow rates and we didn't care about the details of the velocity profile. For this problem, we're trying to actually get a relationship between a particular velocity profile and a volumetric flow rate, so we're going to need to deal with non-uniform velocity profiles. And like we've done in some non-uniform pressure profile problems or some non-uniform shear stress profile problems, anytime you have some non-uniform profile, we're going to need to integrate. So the integrals in the right-hand side, a lot of times we had just sort of you could get the answer for the integrals right away. This one's going to be a little bit more involved. Don't panic. We'll do this together, and the integrals aren't going to be that bad. All things considered, it's just going to be a polynomial, but we're going to need to integrate nonetheless. So this is a sort of more advanced conservation of mass type problem where we're actually going to need to integrate to solve this thing. So here we have it. So let's continue organizing our problem info. Let's say we had some coordinate system, right? And a lot of times when we have pipe-like problems, we might say, hey, there's some center line of this pipe, and we'll do little lowercase r, as some coordinate from the center of the pipe, and we're just going to say z is some direction down the pipe. So little r is sort of our coordinate that's sort of some particular point, some arbitrary point inside the pipe, and we're just going to say capital R is the radius of the whole pipe. So I'm going to make a distinction between capital R, which I'll put in blue as basically like the physical radius of this actual pipe, and little r is sort of a coordinate that defines the position of some point that we're trying to analyze in this pipe. So that's the difference between little r and big R. And let's say that we knew, this pipe is sort of defined by this flow, and we know the max velocity in the pipe, and we also have an expression for what this velocity profile is as a function of radius. So let's say we have this velocity profile within the pipe. We know what the maximum point is, and we can basically say velocity. We're going to give velocity a subscript z because it's a velocity in the z direction, and we're going to put parentheses r because this velocity in the z direction is a function of r, right? For different points r in the flow, the z velocity has a different magnitude, right? Right at the edges of the pipe, there's no velocity at all. Right at the center, it's at its max. So we have this z velocity that is a function of r. And this z velocity as a function of r, again, we're going to derive, right now we're just going to pretend that, we got this velocity profile via magic. Later on in this class, we're going to derive what it is. But here we have it. Vz as a function of r is equal to v max times one minus little r squared over big R squared. So right now, let's say we're given this velocity profile, and we essentially want to say, hey, what is the volumetric flow rate that arises from all of the fluid velocities in this velocity profile? And can we get this volumetric flow rate perhaps in terms of some of these known parameters here? So our goal is to basically get volumetric flow rate, and our goal is to put this in terms of some of the known constants that we have in our equation. So for example, like Vmax, R, etc. So can we get this volumetric flow rate, which as of yet is unknown? Can we put this in terms of known constants from this problem? All right, so there we have it. That's the plan. All right, so we've organized our problem info and we've kind of defined some goals. The next step is going to be to define a control volume. And of course, we're going to use purple to define our control volume. So if we define a control volume, let's do so and define our control volume in a very sensible way. So when we were defining control volumes, it was oftentimes a very good strategy to make surfaces of the control volume coincident with either things that we were looking for or things that we had information about. So for example, I would say we have a lot of information about the walls of the pipe. Why? Because no flow should be going into or out of or through the solid wall of a pipe. Second, we have information about sort of what this velocity profile is at some point within the pipe. So let's also make one of our surfaces this sort of surface that kind of crosses, is a sort of circular surface that's one slice of the pipe. And we'll make that sort of coincident with this velocity profile here. And we'll make another surface here. And of course, we'll make these surfaces sort of straight, right-angled, cutting through the pipe. So the dot products, we anticipate taking dot products when we deal with these, these integrals. Let's make it so these dot products are going to be pretty straightforward to take. So this is going to be our control volume right here. I'm just going to copy it down here so it's a little bit easier to deal with, so we can define our surfaces. So let's give each surface a number here. Let's call this inlet surface 1. Let's call the sides of the pipe, the surface associated with the sides of the pipe, we'll call that surface 2, and then we'll call this downstream surface, surface 3, where there's the velocity, associated with the velocity profile down here. All right, so now we've successfully defined a control volume, and we've done so in a sensible way. We've successfully defined a control volume. We've done so in a sensible way, such that flows are either going to be perpendicular or essentially zero at parts of it to help make the dot products easy. And now I would say we've broken up the surface. We've broken up the surface down here into 3 distinct parts where there are sort of separate phenomena going on, right? Nothing happening at the walls, QV going into surface 1, and this velocity profile coming out of surface 3. So we've kind of broken up the surface into 3 very sensible parts. So we've done our control volume, we've defined our surface. Now let's put down conservation of mass and start dealing with some of these integrals here. So we'll put down conservation of mass right here. So we'll apply conservation of mass to this control volume that we've defined here. So the left-hand side is d dt of the integral over the volume of our control volume of rho dv, and this is equal to negative the integral over the surface of rho times the quantity v dot n dA, and we can of course deal with things here. So strictly speaking, we can have flow that kind of varies, right? You can imagine, let's say I had a heart beating through an artery, instead of just some pipe that was maybe delivering fluid to some bioreactor, or pumping coolant to circulate something, or flow through the syringe of a needle, something like that, right? If I had sort of some pulsatile flow, things get a little bit messy. But for the sake of simplicity, and also to reflect the flows that occur in many bioengineering systems, let's just say that this system is sort of at steady state, right? That I have some constant, non-time varying volumetric flow rate, and that this isn't changing at all with time, right? So let's sort of square away some of our assumptions here. We're going to assume that we have a steady flow. So although steady doesn't necessarily mean that nothing is moving at all, it just means that if I took a snapshot now and took a snapshot later, the velocity profile would look the same, the volumetric flow rate would be the same, all that stuff here, right? So let's assume we have steady flow, and let's assume that we have a constant density fluid, right? We're not dealing with this case where we had one type of fluid in the pipe and we're gradually replacing it with something else. Let's just assume we have this constant density right here. Okay, so we might add a couple more assumptions later on, but let's deal with these for now. So if we have a steady flow, recall that this, I'm actually going to do things out of order. So we were going to deal with integrals on the right hand side, but I'm actually going to switch the order. I'm going to deal with the left hand side first, so forgive me. But you'll see why this helps us out in just a second. So this left hand side here, if you recall, this integral of rho dv, is essentially the contents of this is just how much mass. This term right here is the mass in the control volume. And if I took a snapshot now and then let this flow happen for a while and took a snapshot later, even though new fluid would have entered and old fluid would have exited, the amount of mass in that control volume should be the same, right? It should be the same amount of mass that has always been there, provided it's the same fluid and the same velocities, and the walls of the pipe aren't swelling or anything stupid like that. We have the same amount of mass that we've always had in there. So in this sense, the mass in the control volume is a constant. So pause and ponder. What happens to the whole left-hand side in steady state? So pause and ponder. What happens to this whole left-hand side in steady state? Well, hopefully if you pause and ponder, if I have a constant, something that's not changing with time, the mass in the control volume, and I take its derivative, anytime you take the derivative of a constant, you should get 0. So what's the cool thing about conservation of mass? If you have steady flow if you have a steady, if your system is in steady state, you have some steady flow, something like that, and the left-hand side, you know, no matter what this integral happens to be, it's going to be some constant. I don't even care what it is. I just know that it's a constant. Its time derivative is going to be 0. So this whole left-hand side goes to 0. Why did I want to do the left-hand side first? Well, I don't feel like writing this whole thing out, so I figured let's square it away. Let's put 0 right there. Let's have the system in steady state, so I can just write 0 a whole bunch of times. Whew. Crisis averted. So now let's start dealing with some of these integrals on the right-hand side. If you remember, this is an integral over the whole surface, but I can break up that integral according to the sort of mini surfaces that I've defined, the 3 surfaces that I've defined in my control volume. So what is this going to be? This is basically an integral over surface 1. We're treating rho as a constant, and in this case, let's treat rho as some known constant here. So I'll do rho. And surface 1 is the surface that we're going to sort of deal with. We're going to apply our volumetric flow rate here. So for now, I'm just going to leave it as v dot n dA inside that integral. Then we're going to have an integral over surface 2. And if I think about surface 2, you know, what should v and n be on surface 2? Well, right at the edges of the pipe, you know, fluid can't enter or exit or be dragged along right against the surface of this empty pipe. So, you know, we still have rho on surface 2, but v, velocity, is 0 right at the edge of the wall, because the fluid isn't, it can't, you know, the fluid immediately adjacent to the wall can't be moving. So we just have rho times 0 dA. And then we have surface 3 as well. And surface 3 is going to be, we're going to have rho right here. And then the velocity on surface 3 is this function of r, right? So it's this z velocity that's a function of r. And if vz is going this way and our normal vector is going this way, their dot product basically just yields this vz term that I have here, right? So vz, you know, so vz is pointing this way, n is pointing this way. They're both pointing in the same direction. So their dot product basically just gives me this term right here. So I'll plug in what the actual algebra is, this term right here, but in this case I'll just do vz as a function of r, and we'll have a dA right there. So now let's start dealing with some of these integrals here. So left-hand side, as we had earlier, left-hand side is 0. And because we had this rho is constant, that enables us, remember, if rho is constant, we can pull rho out of any of these integrals. So for surface 1, I have a minus rho out front, an integral over 1 of v dot n dA. Term 2 is 0, so I'm just gonna no longer gonna bother to include that. And now we have this rho times the integral over surface 3 over surface 3. And now I'm actually gonna plug in this, I'm gonna plug in my expression for vz as a function of r into this right here. So plugging that in, I get v max times 1 minus r squared over big R, little r squared over big R squared. And I'm going to have a dA, and we'll deal with exactly what this dA is in just a second. All right, so I have these I have these two terms here. All right, now can we make any further simplifications? Well, yeah, I think we can actually. If you remember from the tank problem that we had earlier, if we had rho out here, the integral of v dot n dA, this was related to this was related to volumetric flow rates, right? So all the terms in the conservation of mass equation are mass flow rates. But if you have density times whatever else is left is going to be a volumetric flow rate. In this case, volumetric flow rate is this QV. That's exactly what we're looking for. But we need to be a little bit careful with the V dot N business here, right? Because QV is basically going into the control volume. N on surface 1 is going to be pointing out. So this term here is related to volumetric flow rate, but strictly speaking, it's the negative volumetric flow rate. So, let's deal with that. So now we basically have 0 is equal to minus rho, and this whole integral essentially just becomes minus QV. And then over here, we have minus, we can pull Vmax out because that's a constant. So now let's have minus rho Vmax times an integral of 1 minus little r squared over big R squared. Times dA. But let's deal with dA right here. So anytime we had a dA, if you remember last time, this is a little area, and we need to think about how, we need to think sensibly about how we're going to break up, this whole surface 3, into infinitesimally small dAs, a whole bunch of infinitesimally small dAs. Right, so how do we break our surface up? So let's imagine surface 3 right here. And if we think about surface 3, when we did dAs in other dimensions, we sort of had a couple of strategies. We basically said, hey, when we were defining a dA, a tip for defining dA is to make it essentially 2 dimensions multiplied against one another, like 2 lengths multiplied by one another, and make one of your lengths d something. And in this case, the length that you make d something, your d whatever, the whatever you put here, you want to make this the variable that you want to integrate with respect to, and the variable that whatever your quantity is varying with respect to. So make d whatever, make this thing the variable that, in this case, velocity varies with. So what variable does velocity vary with? In this case, it varies with r, right? Vz varies as a function of r. Vz varies as a function of r. So the way to break up dA is to have one of our little chunks be dr. So what do I mean by dr? What does dr look like physically? Well, you can imagine if I took this face and I broke it up into a whole bunch of little donuts. Each of these donuts could have some thickness dr, right? So, here's my pipe. I basically break up my pipe into a whole bunch of concentric rings. Each of my concentric rings has a thickness dr, right? But, so what is dA? dA is basically going to be the area of this ring, right? So I have this ring here. dA is going to be what the area of one of these rings. So, and each ring basically has a thickness dr. So, pause and ponder. What is dA if one of the dimensions equals drs, right? So dA equals what? So spoiler alert, one of it's going to be dr, and it's going to be dr times something else that will give us the area, right? So what is the area of one of these concentric rings if it's dr times something? So pause and ponder. Well, what is it? Well, you can imagine if I took this ring and made it infinitesimally thin and then unwrapped it into a little rectangle. If I unwrapped this ring into a rectangle, one of the dimensions is dr, and the other dimension is essentially the circumference of this whole thing. And the circumference of this whole ring, it's going to be different for different rings, right? You know, if I have a ring at the outside, the circumference is different from this ring closer to the center. So this is going to be 2 pi little r, where little r is essentially the coordinate to one point on this ring. And we're making them infinitesimally thin. So what is this? You know, the area is essentially the area of this rectangle if I kind of unwrapped this ring and made it rectangly. So that dA is essentially 2 pi r dr. So there we have it. So what can we do? We can now plug this dA into this expression here, and now we're going to have an integral. It's essentially an integral over this whole surface 3, but we've sliced up this surface 3 into a whole bunch of concentric rings. So we can now sub this dA into here. All right, so what does this look like? Let's start plugging stuff in, right? So we have 0 is equal to rho times QV, and basically these two negative signs cancel out. So we're going to have rho times QV. And now that's going to be equal to, then we have minus rho V max outside of the integral. Then we're going to integrate 1 minus r squared over big R squared. And then instead of dA, we now have 2 pi r dr. So we're not quite all the way there yet. Pause and ponder. What are the limits? What are the limits of integration? What limits of integration should we put on this integral? So take a moment, pause and ponder. Consider, you know, physically what should these limits of integration correspond to? All right, well, hopefully you've paused and pondered. So these limits of integration basically are saying, hey, you know, where do the rings start? Where do the rings go to in such a way that the rings will end up occupying the whole cross-sectional area of this pipe? So what will these rings be? These rings will basically be going from r equals 0, you know, starting with tiny rings that start right at the center, and we'll be kind of adding up all of those rings until we get to the very outer edge of the pipe, and we said, hey, you know, that's basically when little r is equal to capital R right here. So we're integrating from little r equals 0 to little r equals big R. So there we have it. All right, so what can we do? Well, we're getting pretty close to a result here. Is this an integral that we can do? Heck yeah, I think so. So take a moment now, pause and ponder. Go ahead and try to do this integral. Dust off the calculus notes if you have to. You know, see how far you can get. So pause and ponder, go ahead and execute this integral and evaluate it at the limits of integration. All right, so before I actually go ahead and do this integral, I'm going to notice that, you know, I could divide everything by rho and just no longer bother including rho, and I could bring whatever's on this right-hand side, you know, over to the left-hand side and then flip what's my left-hand side and right-hand side. So I can basically do the algebra to solve for QV right now before I even go ahead and do the results of this whole integral. So QV is basically going to be equal to this integral here. So I'm I still have V max out front, and I can pull out this 2 pi as well. So I'm going to do 2 pi V max. If you notice, we're integrating with respect to r, but we have an r here, an r squared here, and a 1 here. When I integrate polynomials, I typically like to distribute, you know, rather than do some sort of like weird product rule integration business, I just like to distribute the r just so it's like one polynomial where all of the powers are pretty straightforward, right? So when I do that, we're going to be integrating from 0 to r. 0 to big R. Now we're integrating r minus r cubed dr. And we still have our 2 pi v max up front. And then when we do this integral, right, when you integrate little r, you get 1/2 r squared. When you integrate r cubed, you get 1/4 little r to the 4th, and this 1 over big R squared is still a constant, right? So we have 1 over big R squared. And of course, we're evaluating this this integral at the limits of integration, which is going to be 0 to big R. So what does that give us? It gives us 2 pi v max times one half big R squared minus 1/4 big R to the 4th over big R squared. And the lower limit of evaluating the lower limit of integration would just give 0 for both of these things, so I'm not going to bother to put it down explicitly. R4 over R squared gives us R squared, so 1/2 R squared minus 1/4 R squared basically gives us 1/4 R squared in here. And then what, so we have a 1/4 big R squared here, the 2 pi out here. What does this give us? This basically says pi times 1/2 v max R squared gives us our result. So, and keep in mind that QV is on the left-hand side. All right, so what does that mean? Well, we can go back. How should we interpret this result? Well, I would say we've already done this to do artist. I'll deal with the left-hand side. I'd say we already did our algebra and organization. So now it's time to do checks. So let's do some checks. If you remember, what checks are sensible checks to do? Well, we like to check for units, right? So if I think about units, volumetric flow rate has to have units of meters squared, meters cubed per second. Pi and 1/2 don't have units. V max is meters per second, and R squared would be meters squared. So the units, check. That's good. What's the second thing? Well, how do these terms, what's the second check we do? The sort of sanity check. How do these terms affect this term right here? Well, if I increased the max velocity of my profile, then that's, it seems pretty sensible that it's going to increase the volumetric flow rate, right? If I increase V max, then the volumetric flow rate should also scale proportionately. That makes sense. What's the other thing? This R squared right here, if I increase the radius of the pipe, now I all of a sudden have a much larger pipe. And if I have a much larger pipe that the fluid is still flowing through, then I'm going to have more flow rate for a given amount of velocity. Right? So the bigger pipe that I have, for the same velocities of fluids going through the pipe, I'm going to have more volumetric flow. So if so all of these results make sense. And in fact, we can actually get we can manipulate things a little bit to further lead to some good intuitions, to interesting results. So let's go ahead and do that. So the interesting results that we can get from this is let's think about the average velocity. The average velocity in this pipe, right? So if I have an average velocity in this pipe, of any fluids, right? V max are the fluids in the middle, the particles in the middle, but the particles at the edge are essentially, zero velocity, right? So in a sense, there should be some average velocity of any particular particle of fluid going through this, right? So in a sense, the average, one way to think about the average velocity is to think about what is the volumetric flow rate divided by the cross-sectional area of the pipe, right? What is the volumetric flow rate divided by the cross-sectional area? In a sense, you know, this is in a sense the average velocity. And if you think the units should line up, right? If I take something with meters cubed per second and divide it by with something with meters squared, that's going to give me meters per second. So if I take the volumetric flow rate and divide it by the cross-sectional area, that gives me the average velocity of any particle of fluid in the pipe. And I can further hash out this relationship here. So I can put in this expression for volumetric flow rate, and of course we know the cross-sectional area of a pipe is pi r squared. So what does that look like? So we have a pi 1/2 V max times r squared, and the area of a pipe would just be pi r squared. So we actually get a lot of interesting things cancel. And it turns out that for this particular situation, where we have this parabolic velocity profile, the average velocity in the pipe is just 1/2 of the max velocity. And it turns out that this is true for fluid in a circular pipe with this parabolic velocity profile. So, you know, this isn't always true for every flow in every vessel, but for this particular case where we have this parabolic velocity profile, it's interesting to find out that the average velocity just happens to be 1/2 of the max velocity. And that's basically because some fluid near the edge is moving slow compared to some fluid moving fast. All right, so hopefully this was a helpful example problem for dealing with conservation of mass. You know, framing a sensible control volume that relates things we don't know to things that we do, breaking up the control volume in a sensible way, being careful with our dot products and making sensible conclusions to the right-hand side, carrying out our integrals, breaking up when we have a variable velocity profile, breaking up part of that control surface, and choosing dA in such a way that our d dimension was the thing that velocity varied with respect to, carrying out our integrals right, you know, doing sensible limits of integration, and then getting a result and doing checks that make sense. So hopefully this was helpful. Good luck with your studies of fluid mechanics. Thanks for watching.